The Great Pyramid of Giza was built with a precision that modern engineers struggle to explain. This video uncovers the invisible inventions, the lost systems of knowledge and organization that made such wonders possible. You will learn the true story of how ancient minds achieved the impossible, a revelation that will permanently change how you see human history. How did they move stones weighing tons with nothing but rope and ramps? What secret mathematics are locked within these ancient walls? By the end, you will understand the hidden genius behind the world's most legendary structures. What do you believe is the greatest legacy of these forgotten builders? The true marvel of the Great Pyramid is not the stone you can see, but the knowledge you cannot. Our modern world is built on patents and blueprints, but the ancients engineered with invisible inventions. These were not physical tools, but the intangible systems of knowledge, measurement, and social organization that made the impossible achievable. Think of it as the software that ran the entire construction project. This included a profound understanding of geometry that allowed them to lay out a perfectly square base on uneven ground, and astronomy that aligned structures with celestial bodies with breathtaking accuracy. Their material science was equally advanced, knowing precisely how to mix mortar or which type of limestone to use for specific loads. These complex systems were not stored in books, but in the minds of master builders, passed down through generations via oral traditions and rigorous apprentice systems. A young worker would spend years learning the secrets of tension and compression, of leverage and plumb lines, not from a manual, but from a master's patient guidance. This foundational concept completely shifts our perspective. We stop searching for a single magical tool and start appreciating the intellectual framework, the collective genius that guided every action. It was this framework that allowed ancient engineers to solve problems with a creativity and precision that still baffles us today. By recognizing these invisible inventions, we move beyond wild speculation and begin to genuinely understand the sophisticated minds behind the monuments. As we peel back the layers of time, we are not looking for a lost device, but for the echoes of a forgotten way of thinking, a weighted string and a basin of water. With tools this simple, the ancients laid the foundations for eternity. The first of these invisible inventions is a pair of devices so fundamental they are almost overlooked: the precision level and the plumb bob. Picture a builder on the Giza plateau, not with lasers and digital readouts, but with a length of string tied to a carved stone weight. This is the plumb bob. When suspended, gravity pulls the weight straight down, creating an unerring reference for true vertical. Every single course of masonry in the pyramid, every towering wall in a temple, was checked and rechecked against this simple truth. For perfect horizontals, they used the water level. By placing water in a long, shallow trough or even a length of hollowed-out wood, they exploited a universal law: water always finds its own level. By marking the waterline at different points across a vast foundation, they could transfer a perfectly flat plane across an entire construction site. The result of this meticulous work is almost incomprehensible. The base of the Great Pyramid is leveled to within a mere inch across its entire 13-acre surface. This was not achieved by chance, but by the repeated, masterful application of these basic tools. Their true genius lies not in the tools themselves, but in the systematic knowledge of how to use them. A novice with a plumb bob gets a roughly straight line. A master builder, understanding atmospheric conditions, the stretch of the cord, and the swing of the weight, could achieve a perfection that challenges our modern instruments. This harnessing of fundamental physics, the pull of gravity, and the behavior of liquids reveals a profound truth. sophistication does not require complexity. It requires a deep understanding of simple, unchangeable principles. From the Americas to Asia, these tools appear in every great building culture, a universal language of precision. With the vertical and horizontal assured by such elegant means, the stage was set for the next great invisible invention, the application of sacred geometry that turned measured stone into celestial architecture. The same ingenuity that harnessed water and gravity was woven into the very fibers of their ropes. While we marvel at the stone, the true lifeline of these projects was cordage, engineered with a sophistication that rivaled modern steel cable. These were not mere strands of plant fiber. They were complex tools, meticulously crafted from materials like papyrus, hemp, and palm fiber, then treated with resins and oils to resist stretching and fraying under almost unimaginable loads. Teams of workers relied on these ropes to haul stone blocks weighing many tons up steep ramps. The secret was not just the material, but the weave, a specific braiding technique that distributed tension evenly across every strand, preventing a single point of failure. Think of a modern climbing rope, its core designed to absorb shock. Ancient ropes were built with the same fundamental understanding of force and durability. Historical carvings and the rare surviving fragments tell us that the Egyptians mastered knots that would hold fast under immense pressure yet could be released with relative ease, a critical safety feature when controlling a multi-ton block swinging in the air. They created de facto pulley systems, looping ropes around wooden posts to redirect force and multiply the effective strength of a team of laborers. This was physics in action, a practical application of mechanical advantage that turned human effort into a precise, controlled lifting force. This deep knowledge of material science and practical mechanics transformed a simple coil of rope into an invisible invention of immense power. It was the indispensable tool that connected human muscle to stone ambition, allowing planners to confidently design structures of a scale that would otherwise be pure fantasy. With the power to lift and move secured by such advanced cordage, the next challenge was one of pure intellect: how to design the entire project without a single sheet of paper or a digital model. A multi-ton block of stone hangs suspended in midair, not by magic, but by the quiet revolution of a rotating drum. The pulley and winch system stands as one of history's most transformative invisible inventions. While the exact archaeological evidence is sparse, the sheer impossibility of raising the massive stones found in temples and pyramids without such a system points directly to its use. Envision a team of workers in ancient Egypt preparing to lift a granite obelisk. They would have employed a wooden crane, a simple yet brilliant device featuring a rotating drum, known as a winch, around which a sturdy rope was wound. This rope was threaded through a wooden pulley, a wheel that changed the direction of the force. The true power of this setup was mechanical advantage. By pulling on the rope, the workers were not lifting the full weight of the stone. The winch acted as a force multiplier, with the lever used to turn the drum, effectively extending their strength. It was a tangible application of physics, where a small, sustained force over a longer distance could overcome a massive resistance. This was not a single, frantic heave, but a controlled, incremental process. Teams would coordinate their pulls, often guided by rhythmic chants or drum beats, slowly walking the rope around the winch to raise the stone inch by deliberate inch. This system provided something equally crucial as power: precision. The slow, measured movement allowed master builders to guide the stone into its final position with astonishing accuracy, seating a lintel or a capstone perfectly onto walls that were already plumb and level. The pulley's evolution was a story of accumulated knowledge. Early versions might have been a single wheel redirecting a rope, but over generations, this basic concept was refined. The addition of the winch and the potential for multiple pulleys working in concert created a technological cascade. Each small improvement, each new understanding of friction and leverage unlocked greater capabilities, allowing civilizations to build taller, grander, and more audacious structures. This invisible invention of coordinated mechanics ensured that the perfectly measured stones could be lifted to their ordained places, setting the stage for the master surveyors who would ensure every element was aligned with the cosmos itself. The sky itself became their ultimate blueprint. While ropes and winches moved the stone, another invisible invention guided its final placement, a suite of surveying tools that turned the celestial dance into terrestrial reality. Under the vast Egyptian night, a priest engineer would use a device called a merkit. This was a simple sighting tool, a narrow, forked bar made of wood or bone, often used with a plumb line. By aligning the fork with a specific star like Polaris or another circumpolar star, and tracking its arc across the heavens, they could pinpoint the celestial pole and establish a true north-south axis with an accuracy that still astounds us. The Great Pyramid's sides are aligned to the cardinal directions with an error of less than 1/15 of a single degree. This was not a lucky guess. It was a result of nights spent in patient, meticulous observation, translating the infinite patterns of the cosmos into a fixed line on the ground. Across the Mediterranean, Roman engineers relied on the groma, a deceptively simple instrument for creating perfect geometry. Picture a vertical staff with a crossbeam, from which plumb bobs were suspended at each end. By sighting across these perfectly vertical lines, a surveyor could mark out straight lines and, even more crucially, perfect right angles across an entire landscape. This was the tool that laid out the relentless straightness of Roman roads and the orderly grids of their legendary military camps and cities. The true power of these tools lay not in their physical complexity, but in the profound knowledge required to use them. A surveyor had to understand the annual movement of the sun to account for seasonal shifts in shadow, the precession of the stars over centuries, and the subtle effects of atmospheric refraction. This was interdisciplinary genius in action, a seamless blend of astronomy, mathematics, and practical craftsmanship. The structures they built were not merely strong, they were harmoniously integrated into their world, aligned with the fundamental order of the universe as they understood it. This deep respect for precision measurement reveals a core truth about these ancient builders. They saw their work as a sacred dialogue between the earth and the sky. How did they encode this celestial harmony into the very proportions of their buildings? The answer lies not in the tools, but in the silent, universal language of mathematics. A single measurement, etched into a rod of black granite, could dictate the rise of an entire civilization. This was the power of the standardized unit, an invisible invention that transformed chaotic individual efforts into a synchronized, empire-wide endeavor. The most famous of these was the Egyptian royal cubit, a length of approximately 20.5 inches, meticulously defined and reproduced on cubit rods for master builders. This was not an arbitrary number. It was derived from the length of the pharaoh's forearm, from elbow to fingertip, a brilliant decision that tied the most important unit of measurement directly to the divine authority of the king. But its true genius was in its reproducibility. A skilled artisan could, in theory, recreate a standard cubit using only his own body and the knowledge of the official standard, ensuring that a builder in Thebes and a quarryman in Aswan were working to the exact same scale. This uniformity was the silent language of monumental construction. It allowed for the precise prefabrication of stone blocks far from the construction site, with the absolute confidence they would fit perfectly upon arrival. Imagine the logistical nightmare of building the Great Pyramid without this, with every team using their own slightly different measure. The structure would have been a mess of mismatched stones and accumulating errors. Instead, the standardized qubit ensured that every block was a compatible piece in a giant, perfect puzzle. This system extended beyond simple length. The Egyptians had smaller units, like the palm and the digit, creating a seamless fractional system for intricate work. This level of organization reveals a society with a powerful central authority capable of enforcing technical standards across vast distances, a form of control as potent as any army. The reliance on the human body for measurement was a global phenomenon. The Roman foot, the Greek fathom, the Japanese shoku, all were rooted in human anatomy, making the tools of construction accessible to every worker. They did not need complex conversion charts, they carried the reference with them. This invisible framework of measurement was the bedrock upon which physical invention could be built, a system of communication as vital as any spoken language. It was this foundational consistency that made the next great leap possible, the creation of tools that could multiply the strength of a single person to move weights that defied belief. "Give me a place to stand, and I shall move the earth." This bold declaration from Archimedes captures the raw power of the lever, a tool so fundamental it feels almost elemental. Yet its application in the ancient world was not a matter of brute force, but of brilliant, calculated finesse. On the sun-baked plateaus of Egypt or the green plains of Salisbury, small teams of workers employed long wooden beams, often fashioned from sturdy sycamore or cedar, to perform what looked like magic. They were not lifting the entire weight of a multi-ton stone. Instead, they were using the lever's simple principle, pivoting the massive block on a carefully placed fulcrum, a stone or a wooden log, to raise one end just enough to slip a roller underneath. This was physics made tangible. The secret was in the ratios, a longer lever arm on the worker's side and a shorter one on the load side meant that their collective push was multiplied into a force far greater than their muscles could ever produce alone. Think of using a crowbar to pry open a heavy crate. That same principle, scaled up to a monumental degree, allowed them to shift stones that would otherwise be utterly immovable. In the quarries of Aswan, where obelisks were carefully separated from the bedrock, levers were the primary tool for the initial, most delicate lift. They provided control. Unlike a sudden, violent heave, leverage allowed for incremental, precise movements. A team could nudge a colossal lintel at Stonehenge into its final seating with gentle, rhythmic pressure, ensuring the stone settled perfectly without cracking or chipping its neighbors. This control was as vital as the power itself, preventing catastrophic damage to meticulously worked materials and protecting the workers from dangerous, uncontrolled shifts in weight. The lever's beauty lies in its universality. From the obelisk makers of Egypt to the trilithon raisers of Britain, cultures separated by continents and oceans independently discovered this same mechanical truth. It represents a cornerstone of engineering intuition, a shared human understanding that a strategic pivot point could redefine the limits of human strength. This invisible invention of applied physics turned impossible tasks into manageable, repeatable processes. But once a stone was pivoted and rolling, how did these builders overcome the ultimate challenge, conquering gravity itself to raise their materials skyward? The answer wins its way upward on a mountain of earth and ambition. A mountain of earth and brick rose alongside the pyramid, a temporary landscape of sheer human will. These vast ramps were the circulatory system of the entire construction project, the invisible invention that made conquering gravity a matter of persistent, steady effort. We often picture a single, straight ramp shooting up one face of the pyramid, but the reality was far more sophisticated. At Giza, evidence points to a complex network of ramps, likely a combination of a long, straight main ramp for the lower levels and a spiraling or zigzagging ramp wrapped around the growing structure for the upper tiers. This design was a stroke of logistical genius. A single, straight ramp to the top would have required an impossible volume of material and become too steep for safe hauling. The spiral or zigzag solution, however, kept the slope manageable, distributing the immense workload across a longer, gentler ascent. These ramps were not permanent monuments. They were temporary, dynamic tools built from the debris of the construction site itself, using mud bricks, gypsum, and limestone chippings. This was sustainable engineering in its most primal form, using what was at hand to solve the problem at hand. Imagine teams of workers hauling a colossal block of granite on a wooden sled. They would pour water or milk in front of the sled's runners, drastically reducing friction and turning a near-impossible drag into a steady, grueling pull. The sound was not of grinding stone, but of sloshing liquid and the synchronized chant of laborers, their collective rhythm turning individual strain into a unified mechanical force. The ramp itself was engineered for stability, with retaining walls and compacted earth to prevent collapse under constant, heavy traffic. Multiple paths and switchbacks prevented traffic jams on this ancient highway to the sky, allowing a continuous flow of materials upward and empty teams to descend without halting the entire operation. This was more than just a slope. It was a masterfully planned and managed supply chain made of dirt. The true invisible invention here was not the ramp itself, but the profound understanding of soil mechanics, friction, and logistics required to design, build, and operate it efficiently. It represents the ultimate translation of simple physics into a landscape-altering tool. Once these perfectly shaped stones reached their destination, how did the builders ensure every single one fit into a flawless, unified whole? The answer lies in the subtle, negative space that defined every block. A perfectly shaped stone block did not always begin as a block of stone. Sometimes it was born as a liquid. The eighth invisible invention transformed raw, formless materials into precision components through the use of specialized molds and formwork. Picture Roman workshops where artisans mixed a potent blend of volcanic ash, lime, and rubble with water to create a revolutionary material, Roman concrete. This slurry was not simply dumped into place. It was carefully poured into elaborate wooden frameworks, temporary cages that gave the liquid its shape and strength as it hardened. This process allowed them to cast not just simple blocks, but entire architectural forms, from the soaring arches of aqueducts to the breathtaking, unsupported dome of the Pantheon. The dome itself is a perfect example, its coffered interior a direct impression of the wooden formwork used to hold the concrete during its long curing process. This was mass production on a grand architectural scale. By creating reusable molds for everything from standard bricks to ornate column capitals, builders could ensure every component was identical, interchangeable, and perfectly fit for its purpose. A brick made in a mold in Gaul would be the same size as one made in Rome, allowing for the rapid assembly of forts, bridges, and cities across the vast empire. This consistency was the physical manifestation of their standardized units of measurement, made real on an industrial scale. But molds were not just for efficiency, they were the key to complex geometry. The curved seating of the Colosseum, the elegant barrel vaults of basilicas, even the intricate decorative elements on temples, all were made possible by carpenters who built these complex negative spaces out of wood. The true invention was not the mold itself, but the foresight to design the hollow space that would guide a formless substance into a perfect, permanent shape. This blend of industrial thinking and artistic craftsmanship allowed empires to build with unprecedented speed and ambition. The very efficiency of this system, however, demanded something else, a hidden network of communication and command that could orchestrate thousands of workers and millions of components across continents. A block of granite is transformed not by a single mighty blow, but by 10,000 patient strikes. The ninth invisible invention is the quiet percussion of the adze and chisel, tools that turned brute stone into refined art. While ramps and levers solved the grand problem of mass and movement, these handheld instruments solved the intricate puzzle of precision. With a chisel made of hardened copper and a wooden mallet, a skilled artisan could shave a stone surface to a perfect, seamless fit. The sound of this work was a constant, rhythmic tapping, the sound of geometry being carved by hand. The adze, with its uniquely curved blade set at a right angle to its handle, was the sculptor's brush. It was perfect for scooping out concave surfaces, for carving the channels that would become perfect joints, or for shaping the curved profiles of columns. The true mastery lay not in the tool's strength, but in the artisan's intimate knowledge of the stone's grain. They knew exactly where and how hard to strike to cleave along a natural plane, removing small, controlled chips rather than causing a destructive fracture. How did they achieve such fine work with metals we consider soft? The answer lies in a continuous cycle of work hardening and sharpening. As a copper chisel was pounded, its edge would become deformed and dull, but the smiths would regularly re-hammer the edge, compressing the metal to make it harder, and then grind it sharp again using abrasive sands. This maintenance was as much a part of the tool as the blade itself. For the final, glass-smooth finish, they employed a different kind of magic, abrasion. Workers would rub the stone surfaces with blocks of quartz or other hard stones, using wet sand as a gritty paste to slowly, methodically polish the surface to a reflective sheen. This is how the hieroglyphs on temple walls were rendered with such crisp, clean lines, each symbol a testament to this painstaking process. This was engineering at the human scale, where the invisible invention was the accumulated skill in the artisan's hands and eyes, a deep, tactile understanding of material behavior. The artistry of these surfaces proves that for the ancients, structural integrity and beauty were two sides of the same stone. But such a vast, thirsty workforce of artisans and laborers could not have functioned for a single day without the final, life-giving invisible invention, the mastery of water itself. The rhythm of 10,000 chisels was matched only by the flow of water, the lifeblood of every great construction site. While stone formed the body of their monuments, water was the vital fluid that made their creation possible. The 10th invisible invention was a comprehensive system of water management, transforming a simple resource into a powerful engineering tool. In the Egyptian quarries, teams moving colossal statues on wooden sleds did not rely on brute strength alone. Historical carvings clearly show workers pouring liquid, likely water, directly in front of the sled's runners. This was a masterful application of physics, using a thin layer of mud to drastically reduce friction, turning an impossible drag into a manageable, steady pull. The sound was not of grinding wood, but of slick mud and coordinated effort. But water's role went far beyond lubrication. Quarrymen discovered that by driving wooden wedges into natural fissures in the bedrock and then soaking the wood, they could harness a surprising force. The saturated wood would swell with tremendous pressure, cleanly splitting the stone along a predetermined line. This clever technique allowed them to extract perfectly shaped blocks with remarkable efficiency, using nature's own forces to do the hardest work. On the construction site itself, a network of drainage channels and reservoirs was just as critical as any ramp. These systems ensured the foundation trenches remained dry and stable, preventing catastrophic collapse from a sudden downpour or groundwater seepage. The Romans elevated this practice to an art form, building temporary aqueducts to bring fresh water directly to their laborers, sustaining the immense workforce, while sophisticated sewers carried waste away, maintaining hygiene and preventing disease. They even channeled water to power mechanical saws for cutting stone and to create canals for floating heavy materials right to the project's edge. This holistic mastery of hydrology reveals a profound truth about these ancient engineers. They did not fight against their environment, they partnered with it. They saw a river not as an obstacle, but as a potential transport route, and rainwater not as a nuisance, but as a tool for shaping the land itself. This seamless integration of natural forces with human ambition required one final, overarching system of thought, a silent language that could translate a visionary idea into a perfectly proportioned, timeless structure. The silent language of mathematics gave form to their greatest ambitions. Long before the first stone was cut, ancient architects were solving complex equations, embedding timeless geometric principles into the very soul of their designs. This was the 11th invisible invention, the application of sacred geometry and proportional systems. Structures like the Parthenon in Athens were not merely built, they were composed using ratios like the golden ratio, a specific mathematical relationship believed to represent perfect harmony. This created a visual balance that feels instinctively right to the human eye, where every column, every space is in a perfect relationship with the whole. In Egypt, the Great Pyramid seems to encode both pi, the fundamental constant of a circle, and phi, the golden ratio within its angular proportions. This was not a coincidence. It was a deliberate act of philosophical engineering, ensuring a building was not only structurally sound but also spiritually resonant, a bridge between the earthly and the divine. These rules were the true blueprints, often transmitted through simple diagrams drawn in the sand or small-scale models made of wood or clay. A master builder could point to a diagram and explain that the height of a pillar must be precisely 8 times its base width, or that the chambers of a temple must align on a specific triangular grid. This system allowed for perfect scalability. A small handheld model governed by these unchangeable ratios could be enlarged 100-fold into a mountain of stone with the certainty that its proportions would remain perfectly harmonious. The invisible invention was this shared intellectual framework, a set of rules that allowed an abstract concept of divine harmony to be translated into a physical, breathtaking reality. It was the ultimate tool for turning vision into monument, but these perfectly proportioned stones, once designed, demanded a final, physical invention to lift them into the sky, a machine that would harness human strength with brilliant efficiency. A wooden arm swings against the sky, a silent pivot point that redefined the limits of construction. This was the birth of the crane, an invisible invention that moved building from the ground into the air. While the Egyptians mastered the ramp, it was the ancient Greeks who perfected the crane, transforming it from a simple lifting device into a sophisticated machine. Picture a wooden tripod supporting a rotating boom, a thick rope wound around a winch drum, and a team of men pulling in unison. This system was a symphony of simple components working in concert. The winch provided the mechanical advantage, a rotating drum that acted as a force multiplier, allowing a small, steady pull to lift a tremendous weight. The rope, engineered for strength, ran through a wooden pulley, a wheel that gracefully redirected the force, minimizing friction and maximizing control. The true genius of the crane was its ability to operate in confined spaces where a massive earth ramp was impossible. It allowed builders to place heavy stone blocks, like the massive architraves of the Parthenon, with pinpoint accuracy high atop a forest of columns. This was not just about lifting, it was about precision placement. a master builder could guide a multi-ton block, gently nudging it into its final seating with an intimacy that a ramp could never provide. The archaeological proof is etched into the stones themselves. Look closely at marble blocks from Greek temples, and you will find precisely carved lifting holes, called Lewis holes, where the iron claws of the crane would grip the stone securely. Vase paintings from the era sometimes show these very contraptions in action, depicting a god being hoisted into place, a mythological nod to a very real technological revolution. This shift from ramp to crane was monumental. It freed architecture from the tyranny of earthen slopes, enabling the delicate, vertical elegance of classical temples. It made construction safer, reducing the risk of catastrophic collapses on steep inclines and allowing work to proceed on multiple levels simultaneously. The crane represents a fundamental leap in thinking, a move from conquering gravity with mass to outsmarting it with mechanics. It was the optimization of human power through brilliant design, a testament to the problem-solving drive that turns a simple lever and rope into a tool that could touch the heavens. Yet, before any crane could lift a stone skyward, that same stone had to travel miles across the earth, a journey made possible by an even more humble invention. A colossal stone glides across the desert, not on wheels but on a path of moving logs. This simple yet brilliant system of rollers and sledges transformed impossible transport into a coordinated, rhythmic process. The principle was pure physics in action. By placing a series of sturdy tree trunks, often cedar or acacia, beneath a heavy load resting on a wooden sledge, workers created a temporary, renewable road. As teams pulled on ropes attached to the sledge, the stone would move forward, and the rollers behind it would be carried to the front, creating a continuous loop of motion. This dramatically reduced the friction that would have made dragging the load directly on the ground an insurmountable task. The sledge itself was a critical component, a robust wooden platform that distributed the immense weight of the stone evenly. This prevented the block from cracking under its own pressure and protected the prepared pathway from being gouged and ruined. On Easter Island, this very method was likely used to transport the iconic Moai statues, their stone gaze slowly advancing across the island on a bed of rolling timber. In Mesopotamia, the same principle moved the giant Lamashu figures that guarded palace gates. The entire operation was a symphony of coordination. One team would haul the ropes, another would guide the stone to keep it on course, and a third, often the most nimble workers, would constantly dash back and forth, retrieving the freed rollers from the rear and sprinting to place them ahead of the advancing sledge. This required immense stamina and perfect timing, a logistical dance that turned individual effort into a single, flowing machine. The efficiency of this system is staggering when you consider the distances involved. Egyptian obelisks, some weighing over 400 tons, were quarried in Aswan and transported hundreds of miles north to their final homes in temples like Karnak. They accomplished this not with magic, but with the relentless, grinding logic of the roller. This invisible invention demonstrates a profound understanding of material behavior and force, turning the simple act of rolling a log into the key that unlocked continental-scale construction. But the success of these rolling pathways hinged entirely on the surface they traveled over, a challenge that would inspire one of the most enduring legacies of ancient engineering. A colossal stone block's journey did not end at the quarry's edge. It simply transitioned onto a highway of human ingenuity. The creation of specialized roads and transport pathways stands as a testament to the ancient world's grasp of logistics, an invisible invention that turned impossible distances into manageable supply line. These were not mere dirt tracks but engineered causeways, meticulously constructed to bear weights that would crumble an ordinary path. For the pyramids, the Egyptians built vast, stone-paved roads that ran from the Nile's edge directly to the rising construction site. These causeways were reinforced with timber and compacted rubble, creating a stable, unyielding surface for the heavy sledges and their multi-ton cargo. The surface was often lubricated with water or clay, transforming the grueling haul into a steady, controlled glide. But the engineering went far beyond a simple flat road. The gradients of these pathways were carefully calculated, presenting just enough of an incline to be manageable for large teams, yet never so steep as to risk losing control of the precious stone. Every turn was a planned curve, designed to allow the long sledges to navigate without jamming or toppling their load. This was civil engineering on a monumental scale, where the journey itself was a critical component of the architectural plan. The Romans would later perfect this concept, building their legendary road networks that served both military and trade purposes, but the principle was born from the need to move the unmovable. The sheer investment in these temporary but vital structures reveals the profound long-term planning behind every megastructure. It underscores a fundamental truth: the transport route was as critical to the project's success as the foundation of the building itself. These durable pathways, capable of surviving the relentless passage of thousands of stones, point to another layer of mastery. What tools could possibly shape and maintain such resilient infrastructure, or quarry the stone in the first place? The answer lies in the fire and forge, in the creation of metal tools hard enough to challenge the very bones of the earth. The rhythmic tap of a bronze chisel against granite was a declaration of war against the very fabric of the earth. This was the cutting edge of ancient engineering, the 15th invisible invention, metal tools that turned impassive stone into architectural language. While we marvel at the stone itself, it was the development of copper and later bronze, saws, chisels, and drills that gave builders the vocabulary to speak in blocks and columns. These metals were softer than modern steel, a fact that makes their achievements seem almost paradoxical. How could a copper saw possibly cut through granite? The secret was not in the metal alone, but in the partnership between the tool and the earth. Workers used these saws with a constant stream of an abrasive slurry, a gritty paste of water and quartz sand. The saw itself did not cut the stone. Instead, it dragged the incredibly hard quartz particles across the surface, and it was these tiny, sharp grains that did the actual cutting, slowly and methodically grinding a groove through the toughest granite. It was a slow, patient process measured in millimeters per hour, but it was a process that yielded perfect, controlled results. The same principle applied to drilling. A hollow copper tube, rotated back and forth with a bow-like tool, would be fed with the same abrasive slurry. The tube would not drill a solid cylinder of stone, but rather grind a circular groove, leaving a perfect core inside that could be broken free. This technique allowed for the creation of precise holes for dowels, or for the intricate hollowing out of stone vessels. The tools themselves were not static. They were constantly maintained and improved through a process called work hardening. As a copper chisel was pounded, its cutting edge would become deformed, but this very deformation compressed the metal's crystalline structure, making it harder and more durable at the point of impact. Artisans would regularly re-hammer and resharpen their tools, understanding this cycle of use and renewal intimately. The transition to bronze, an alloy of copper and tin, was a revolutionary leap. Bronze was inherently harder, held a sharper edge for longer, and could be cast into more complex and efficient shapes. This material innovation unlocked new possibilities, allowing for the quarrying of even harder stones like basalt, and the creation of intricate hieroglyphs and reliefs with crisp, clean lines that have survived for millennia. The ability to shape stone with such accuracy was the bedrock of everything that followed. It allowed for the creation of interlocking blocks that fit together with seams thinner than a razor blade, distributing weight perfectly and creating structures of immense stability. It enabled the decorative elements that transformed a building from a mere shelter into a story written in stone. This mastery of metallurgy, however, points to a system far larger than any single quarry or workshop. The tin needed for bronze was not found everywhere. It required vast, interconnected trade networks stretching across continents. The very existence of these metal tools whispers of a hidden world of merchants, miners, and smelters, an organizational machine that fueled the architectural one. A single misplaced number could bankrupt a kingdom. While master builders directed the placement of stone, another class of specialists managed the very soul of the enterprise, the endless river of numbers. Their tool was the abacus, a simple frame of beads on rods that served as the ancient world's calculating engine. Picture a royal scribe in Egypt, seated before a pile of papyrus scrolls, his fingers flying across a wooden counting board. He is not guessing, he is precisely tallying the thousands of limestone blocks delivered from the quarry this month, calculating the rations of bread and beer needed to sustain the army of workers for the next season, and estimating the copper required to keep every chisel sharp. This was high-stakes data management, and the abacus made it possible. By sliding beads along wires or moving counters on a marked table, a skilled user could perform complex addition, subtraction, and even multiplication at a speed that rivaled mental calculation. The rhythmic click of the beads was the sound of logistics, the translation of raw materials and human labor into a controlled, predictable plan. This intellectual tool was universally adopted, from the grain warehouses of Mesopotamia to the treasuries of Rome. It allowed administrators to answer critical questions with confidence. How many tons of stone are still needed to complete the third course of the pyramid? How many man-days of labor will it take to dress and set them? The answers derived from the abacus dictated the flow of resources across entire empires. This was the birth of project management, an invisible invention of pure organization that turned a visionary design into a scheduled, budgeted, and achievable reality. The success of a megastructure did not rest on genius alone, but on the meticulous, data-driven coordination of every single element. Yet this administrative framework, this system of numbers and accounts, would have been utterly useless without the living, breathing knowledge it was built upon. The true repository of this wisdom was not a scroll or a counting board, but the mind of a master craftsman, patiently teaching his apprentice the secrets of the trade. A master's patient hands guide a young apprentice's grip on a chisel, passing down a craft that would outlive empires. This living chain of knowledge, the system of apprenticeship, was perhaps the most vital invisible invention of all. It was the human engine that powered every other innovation. A boy, perhaps only 12 years old, would enter the service of a master builder for years, even decades. He did not learn from books or blueprints, but through direct physical experience. He would begin with menial tasks, mixing mortar or hauling water, all the while watching the masters at work, absorbing the rhythm of the site and the language of the tools. Slowly, he would be trusted with more complex duties, learning to dress a stone, check a plumb line, or tie the critical knot that would hold a multi-ton block. The knowledge transferred was not merely technical, it was deeply cultural and spiritual. An apprentice in Egypt learned that the pyramid was not just a tomb, but a vehicle for the pharaoh's soul, a resurrection machine. A stonemason in medieval Europe understood that carving a gargoyle was an act of devotion, a way to ward off evil spirits from the sacred space. This embedded meaning transformed labor into a sacred act, ensuring a level of care and precision that went far beyond simple wages or orders. This system created a stable, self-correcting repository of engineering wisdom. A master builder carried the accumulated knowledge of his teachers and their teachers before him. When a new problem arose, like quarrying a particularly stubborn type of granite, the solution was not invented from scratch. It was drawn from this deep, communal well of experience. Each generation could then refine these techniques, making small, incremental improvements that, over centuries, led to staggering leaps in capability. The breathtaking consistency in style and quality seen in structures built hundreds of years apart, like the temples of Karnak, is a direct result of this unbroken chain of mentorship. The true product of this system was not just a building, but the next generation of builders, armed with the invisible tools of geometry, intuition, and a profound respect for their craft. This human network of teaching and learning ensured that the stars themselves could be mapped onto the Earth with unwavering accuracy for generations. How did they codify the cosmos into a language their tools could understand? The stars were not just lights in the sky, they were the fixed points on a celestial blueprint. This final class of invisible invention, the astronomical alignment instrument, turned entire structures into permanent stone calendars. Under the deep velvet of an Egyptian night, a priest engineer would set up his merkit, a simple forked sighting bar used with a plumb line. By aligning the fork with a specific star and tracking its path, he could establish a true north-south axis with an error of less than 1/15th of a single degree. This was not a one-night task. It required years of patient, meticulous observation, building a long-term data set of the heavens' slow dance. Across the sea in Greece, a device of staggering complexity, the Antikythera mechanism, performed calculations that would not be rivaled for 1,000 years. This bronze assemblage of gears and dials acted as an analog computer, predicting lunar phases and eclipses, providing the precise timing needed for rituals and constructions aligned with cosmic events. These tools allowed builders to encode cosmic cycles directly into their architecture. A temple doorway might be positioned so that the dawn light of the solstice illuminated only the inner sanctum once a year, or a series of pillars could cast shadows that marked the equinoxes. The structure itself became the instrument, a permanent observatory that tracked time itself. This integration of astronomy and construction reflects a world-view where the earthly and the divine were inseparable. To build in harmony with the cosmos was to participate in a sacred order, adding a profound spiritual dimension to every precisely laid stone. This celestial focus required an equally precise earthly connection, a way to ensure that these cosmically aligned stones would hold fast for eternity, locked together by the hidden strength of metal and joinery. Molten metal flowed like liquid light into the grooves of waiting stone. This was the art of the dovetail clamp, an invisible invention that locked entire structures together against the relentless pull of time and earth. Greek and Roman engineers carved precise, interlocking channels into the faces of massive stone blocks, creating negative spaces in the shape of a dove's tail or a double T. They would then pour molten iron or lead directly into these prepared cavities. As the metal cooled and solidified, it became a permanent, unyielding grip, a metal fist clenched deep within the stone, binding neighboring blocks into a single, unified mass. This was not a simple glue, it was a structural partnership. The primary enemy was not just gravity, but the subtle, shifting dance of the Earth itself. In earthquake-prone regions like Greece and Anatolia, these clamps prevented stones from sliding past one another during tremors. They also countered the slow, inevitable settlement of massive foundations, ensuring that walls and columns remained perfectly aligned for centuries. The process demanded incredible precision from the stonemasons. Each channel had to be carved to exact dimensions so the poured metal would fill it completely, creating a perfect, seamless fit. This technique distributed mechanical stresses evenly across the entire joint, preventing points of concentrated pressure that could cause a crack to propagate and lead to catastrophic failure. The clamps turned a collection of individual stones into a monolithic, cooperative structure. This early form of reinforcement reveals a sophisticated understanding of structural dynamics. Builders recognized that stone, while strong in compression, could be vulnerable to shearing and tensile forces. The metal clamps addressed this inherent limitation, adding a flexible strength that pure masonry lacked. By combining materials, they created a composite system far more resilient than the sum of its parts. This clever exploitation of material properties unlocked new architectural ambitions, allowing for wider arches, more slender columns, and taller walls that could confidently resist the elements. The very presence of these metal bones within stone bodies points to the final protective step in their grand designs. How did they ensure that these iron ligaments, so vital to structural integrity, would not themselves be consumed by rust? The answer lies in a final, invisible shield, a barrier between the hard-won achievement and the relentless patience of the air. A final, invisible shield was brushed onto the stone, a liquid armor against the patience of the elements. These protective coatings and surface treatments were the ancient world's answer to long-term preservation, a sophisticated blend of chemistry and aesthetics. Workers would apply washes of slaked lime, creating a brilliant white surface that not only looked pristine but also sealed the porous limestone beneath, preventing water from seeping into the microscopic cracks where it could freeze, expand, and slowly tear the stone apart. In Mesopotamia, builders used bitumen, a naturally occurring tar, to waterproof everything from foundation bricks to the hulls of river barges, understanding its remarkable impermeability. The Egyptians perfected gypsum plasters, mixed to a smooth, buttery consistency, to create flawless surfaces for their vibrant hieroglyphs, ensuring the stories of the gods would endure. Each of these treatments served a dual purpose. A coat of lime wash was not merely protective, it was also highly reflective, bouncing the harsh desert sunlight off a temple's walls and significantly reducing heat absorption, which helped to maintain a stable internal temperature. This was passive climate control engineered centuries before the term existed. The true chemical genius, however, emerged with the Romans and their pozzolana-based concrete. This volcanic ash, when mixed with lime and water, triggered a chemical reaction that allowed the concrete to cure and harden even when completely submerged. This revolutionary material did not just resist water, it thrived in it, enabling the construction of harbors, bridges, and aqueducts that have withstood the constant assault of waves and weather for 2 millennia. The development of these coatings was not accidental. It was the result of generations of experimentation with local materials. Someone, long ago, discovered that a certain clay, when fired and mixed with water, created a durable seal, or that a specific plant resin could protect wood from insects. This accumulated knowledge of material interactions was a priceless, invisible invention in itself. It reveals a mindset that looked far beyond the completion date, an engineering philosophy where the legacy of the structure, its ability to stand for ages, was as important as its initial grandeur. This meticulous attention to preservation required a workforce that was not only skilled but also precisely coordinated. The application of these plasters and washes had to be timed perfectly with the construction schedule, a complex dance of labor that relied on the steady, unchanging rhythm of time itself. The steady drip of a water clock measured more than just hours. It orchestrated the rhythm of an entire civilization at work. On the sprawling plateau of Giza, the shadow of a sundial creeping across a marked stone divided the long day into precise shifts for thousands of laborers. This invisible invention of systematic timekeeping was the metronome of monumental construction, transforming a chaotic crowd into a synchronized machine. Supervisors used these devices to coordinate complex, interdependent tasks. The mixing of gypsum mortar had to be perfectly timed with the arrival of a new shipment of limestone blocks. The teams hauling stones up the ramps needed to clear the path before the polishing crews began their delicate work on the newly set courses. A water clock or clepsydra, with its regulated flow from one marked vessel to another, provided a reliable measure even after sunset or on cloudy days, enabling work to continue in shifts around the clock if necessary. Historical records from Babylon to Rome detail the use of these timekeepers, not just for rituals but for the pragmatic management of massive labor forces. In Rome, the blast of a horn or the ringing of a bell, timed by a sundial, would signal the change of shifts, the break for meals, and the end of the workday. This prevented the exhaustion of crews and ensured that critical, time-sensitive processes like pouring concrete that required continuous placement were never interrupted. The division of the day into manageable periods was a stroke of psychological genius as much as logistical planning. It gave workers a clear structure, making an overwhelming project feel achievable through a series of defined, completable tasks. This emphasis on scheduling reveals a level of project management sophistication that rivals any modern construction site, rooted in a deep cultural value for order and precision. With the entire workforce moving to the beat of a single, measured timepiece, the final challenge was one of pure foresight, translating a grand vision into a practical, step-by-step guide that every worker could follow. A miniature world of clay and wood held the secret to building on a colossal scale. Before a single foundation trench was dug, ancient architects crafted detailed scale models, three-dimensional blueprints that brought their grandest ideas down to a human, manageable size. In a sunlit Egyptian workshop, a master builder would sculpt a tiny temple from Nile mud, carefully shaping its columns and courtyards. This was not a toy, it was a vital planning tool, allowing him to walk around his design, to see how the shadows would fall at different times of day, and to identify potential weaknesses in a wall or the awkward angle of a corridor long before it was immortalized in stone. These models enabled a form of virtual construction, a safe space for experimentation where proportions could be adjusted and structural elements tested without the catastrophic cost of a real-world failure. For the workers, a model was a universal language. A laborer who could not read hieroglyphs could look at a miniature pylon and understand exactly what he was helping to create, ensuring that every single person, from the quarryman to the high priest, shared a common vision for the final product. This practice of pre-visualization was supported by precise, two-dimensional plans. Archaeologists have found fragments of papyrus and limestone flakes, known as ostroka, covered in grid-based drawings of tomb layouts and pyramid cores. These grids were the key to scalability, a mathematical framework that allowed a small sketch to be enlarged with perfect proportionality into a structure reaching for the clouds. A line that was 2 squares long on papyrus could become a wall 200 cubits long on the ground, with every angle and corridor preserved. This combination of model and plan represents the crystallization of thought, the moment an abstract concept was translated into a tangible guide for action. From the clay house models of Mesopotamia to the wooden temple prototypes of Greece, this invisible invention of scaled prefiguration was a universal step in the journey of creation. It provided the confidence to build big because the builders had already seen their work completed in miniature. Such ambitious visions, however, demanded more than just local stone and timber. They required a global network of resources, a hidden web of trade that spanned continents. A ship laden with cedar from Lebanon was as crucial to a pharaoh's ambition as any chisel or ramp. These sprawling trade networks formed the supply lines of antiquity, an invisible invention that connected continents through a shared hunger for perfection. Local stone and timber were often not enough for the grandest visions, demanding specialized materials only found in distant lands. The cedars of Lebanon provided long, straight beams of incredible strength, perfect for the massive sledges that hauled obelisks and the towering roof spans of great temples. Obsidian from Anatolia offered a glass-sharp edge for fine ceremonial tools and detailed carving work, while copper from the Sinai Peninsula and later tin for bronze, sourced from as far away as Afghanistan, fueled the entire metallurgical enterprise. This was not haphazard barter, but a highly organized system of logistics and diplomacy managed by powerful central authorities. Royal emissaries negotiated treaties with foreign kings, securing not just materials, but also the safe passage for merchant convoys across deserts and seas. The Roman appetite for marble is a perfect example, with emperors sponsoring quarries in Egypt for imperial purple porphyry, in Greece for pristine white Pentelic marble, and in modern-day Turkey for richly colored Pavanazetto. Their cities became a glittering mosaic of the Mediterranean's geological wealth, a direct result of this managed globalism. This interconnectedness allowed for unprecedented architectural diversity and resilience. A builder was no longer limited by what was in his own backyard. He could draw upon the finest stones, the strongest woods, and the most durable metals from across the known world. The stability of these routes created a kind of ancient globalization, where the success of a pyramid in Giza was subtly linked to the mining operations in the Sinai and the forestry practices in the Levant. But such an extensive web of commerce, moving priceless cargo over vast distances, required a final, foundational invention to fuel its engine. How did ancient kingdoms pay for it all, transforming raw material into monumental ambition without a single coin or bank transfer? A pharaoh's decree could redirect the entire wealth of a nation toward a single, silent mountain of stone. The mobilization of an ancient economy stands as one of history's most potent invisible inventions, a system where taxation and tribute were not merely for royal luxury, but the very fuel for monumental ambition. In Egypt, the state functioned as a colossal engine of resource allocation. Scribes meticulously recorded every contribution, from a farmer's bushel of grain to a region's quota of laborers, all flowing into the centralized project of pyramid building. This was not slavery in the simple sense, but a form of national service, a corvée labor system where citizens fulfilled their duty to the god-king during the Nile's annual flood, when farming was impossible. Their work was compensated with rations of bread, beer, and cloth, a sophisticated wage system that sustained a massive, non-agricultural workforce for decades. The Roman state perfected this model on an imperial scale. The vast treasuries filled with taxes from conquered provinces were directly channeled into engineering marvels that defined their civilization, from the aqueducts that fed cities to the forums that centralized civic life. This centralized economic control allowed for the accumulation of capital and materials on a previously unimaginable scale. It turned the abstract concept of a temple or a pyramid into a budgeted, scheduled reality. The true genius lay in the prevention of waste and shortage. Administrators used their counting boards and scrolls to forecast needs with stunning accuracy, ensuring that the quarries never ran ahead of the transport crews and that the food supplies never failed the workers. This economic framework reveals a profound truth. The grandest technological achievements were underpinned by sophisticated societal structures. Wealth was not hoarded, but strategically channeled into legacies of stone and mortar, creating public works that stabilized the state and glorified its rulers for millennia. This flow of physical resources, however, was always accompanied by a parallel current of meaning, a symbolic language that transformed engineered stone into a vessel for the human spirit. A ceremonial axe never meant to cut stone could consecrate the very ground on which a temple would stand. Across the ancient world, the act of building was as much a spiritual undertaking as a physical one, and the rituals performed with symbolic tools were considered essential to a structure's longevity and power. Before the first foundation trench was dug, priests and elders would gather at a chosen site for a profound ceremony. They would bury sacred objects in deep pits, creating what archaeologists call foundation deposits. In Mesopotamia, these might be inscribed clay tablets calling upon the gods for protection, or small, beautifully carved figures of protective deities. In Mesoamerica, the Maya placed ritual caches of jade, obsidian, and shells beneath their towering pyramids, offerings to the gods of the underworld and the sky. These objects served as metaphysical anchors, tethering the physical building to the cosmic order and ensuring its place within a divinely sanctioned reality. The tools used in these rites were charged with meaning. A ceremonial axe carved from a single piece of jade was not a functional woodcutting tool, but a symbol of royal authority and a connection to the divine. Its purpose was to symbolically cut the boundary between the profane world and the sacred space of the future temple. Similarly, a priest might use a golden trowel to lay the first symbolic brick, an act that sanctified the entire construction process that would follow. This integration of ritual provided something intangible yet crucial to the workforce, a shared sense of purpose that transcended daily labor. For the thousands of workers hauling stone, the knowledge that their work was blessed by the gods and would serve a higher cosmic function transformed back-breaking effort into a sacred duty. It fostered a powerful social cohesion, uniting people from different backgrounds in a common spiritual endeavor. This symbolic dimension reminds us that these megastructures were never just buildings. They were prayers in stone, carefully engineered bridges between the human and the divine. The invisible inventions of ritual and meaning were, in their own way, as vital as the lever and the ramp, for they provided the unwavering belief that made the impossible seem achievable. How did these deeply held beliefs, encoded in ritual and geometry, ultimately shape the final, breathtaking form of the world's most legendary structures? The principles that lifted the pyramids are now encoded in the steel and silicon of our modern world. Ancient leverage is the same physics that allows a crane to hoist an I-beam 50 stories high, and the Roman understanding of the arch is the direct ancestor of the graceful spans of our longest bridges. Contemporary engineers actively study the chemical composition of Roman concrete, searching for clues to create more durable and environmentally friendly building materials today. The invisible inventions of standardized measurement have evolved into the intricate global system of building codes and specifications, ensuring that a skyscraper in Dubai meets the same rigorous safety standards as one in Tokyo. This is not merely a historical echo. It is a continuous lineage of problem solving. The ancient system of apprenticeship, where a master passed knowledge to a novice, has been formalized into our modern universities and vocational schools, preserving and advancing the collective wisdom of the craft. The true legacy of these invisible tools is their timeless logic, the fundamental understanding of force, material, and organization that remains as relevant on a computer-aided design screen as it was on a papyrus scroll. We are still building on the intellectual foundations they laid, proving that the most enduring inventions are not made of stone but of thought. This profound connection across millennia invites a final, unifying question. How do all these disparate threads of genius, the Plumb bob and the pulley, the celestial alignment and the economic system, weave together into a single, coherent picture of human achievement? The echoes of ancient genius are not silent. They resonate in the very principles that shape our modern world, from the cranes that define our skylines to the global supply chains that build them. Our journey through these invisible inventions reveals a universal truth that the greatest structures are born not from magic, but from a profound mastery of the possible. It was the creative application of simple physics, the meticulous organization of thousands, and a deep spiritual connection to the cosmos that turned stone and ambition into eternal wonders. This legacy challenges our own assumptions about progress. True ingenuity is not always about newer, more complex technology, but often about a deeper, more insightful understanding of the fundamental tools already at our disposal. The collaboration between the surveyor with his sighting tool and the laborer with his rope, the synergy between the astronomer priest and the master quarryman, shows us that human achievement at its peak is always a collective symphony. As you look at the world around you, consider how the ancient principles of leverage, precise measurement, and shared purpose can inspire solutions to the challenges we face today in sustainable building, thoughtful urban planning, and collaborative innovation. The invisible inventions of the past are a timeless blueprint for the future. We would love to hear which of these ancient innovations most surprised you, so please share your thoughts in the comments below. If you enjoyed this exploration into the hidden foundations of history, subscribe for more journeys that uncover the world's greatest mysteries. Thank you for joining this investigation into the invisible tools that built legendary wonders, and may it forever deepen your appreciation for the quiet, collaborative genius of humanity.